Hello again. Yeah, I did some troubleshooting, meaning basically I will put the task manager and the disk usage was like 100%. So what's going on? So I looked up in the internet in my cell phone and I did what they told me to do. And yeah, I think it's better now. So yeah, I really appreciate those computer programmers and IT personnel who write these articles in the internet. Of course, they get some advertisement revenue, but still, right? Yeah, it's great. So, so um, so during when I was troubleshooting this computer, right, there's some lag time in between, so when I was waiting for computer to respond, yeah, I thought about this general relativity a little bit, and it seems the concept of ether can be very useful here. Okay, so I haven't started writing the general relativity disproof part yet because that's going to be real. That's another chapter in this paper. Okay, and I by now I think it's bigger than it will be bigger than what I initially thought it would be. Okay, so it's good that I didn't start writing the general relativity disproof because it seems there's more to it. All right, so yeah, we will brainstorm here and then we think things through before we start writing. Okay? Okay. Right, let's take 5 minutes. Huh? Yeah, this computer is doing a lot better. Okay, good. Before it was like stop freeze kind of. Okay. Yeah, I think my computer is better now. Okay. Hmm. All right. Okay, so computer didn't crash yet. I mean, the software didn't crash yet. Good. I mean, I used to be a computer programmer. That's of course that's different from IT, information technology. Okay, because not every IT professionals do computer programming. Yeah, they do shell script, this operating system or MS DOS. What's that called? I forgot. I used to know. Okay. Yeah, I did some of that too back in the days. Okay, but yes, computer programmer, IT professionals is there's some overlap there. Okay, so yeah, I can troubleshoot my computer by looking at the internet website that explains step by step. Okay, yeah. Hmm? Yeah. Because when I was working as a computer programmer, people come to us, so we kind of played some part of IT role too, but yeah, so I'm quite familiar with that. Okay, give me 1 second. Let me get some Tums. Yeah, I'm gonna start drinking a little bit. Okay, so so yeah, let's start giving some acknowledgement of Mr. Einstein's contribution. Okay, let's pay him some tribute. Okay, he asked the right question. He just got the answers wrong. Right? But asking the right questions in itself is very big contribution to science. Yeah. Yeah. Here's the right question. Yeah. We admit his contribution. Okay. It's kind of honoring our parents, kinda. Okay. I mean, unless Einstein asked this question and he answered it wrong, yeah, we wouldn't be discussing this. Special general relativity disproves. Okay, but he has the right questions. Okay, so he just answered it wrong. So yeah, we'll finish up what he started. Okay, because he didn't quite do that. Like yeah, unified field theory. Okay, so uh, so I was watching in YouTube his documentary. Okay, um, a lot of physics professors made some commentary in that documentary. It's in YouTube. Okay, I did make citation to that YouTube video in my paper. Okay, our paper. Yeah, it's very nice documentary. It's very educational, and of course, in their mind, yeah, they thought Einstein is right, but still, it was very informational video. Okay, so in the documentary, they said they mentioned Einstein saying he saw the experiment if elevator have this cable, right? If the cable is cut, then the person inside of this elevator will not feel any kind of gravitation, just like astronauts out in the space in a spaceship. Okay, so let's examine that whether that's true or not. Okay, right. Later on we will. Okay, now the when it comes to acceleration, yeah, just think about the airplane taking off in the runway, right? When it takes off, yeah, huge acceleration. So our body like pulls back like this, right? And let's assume that there's constant acceleration, okay? Like 9.8 meter per second squared or something like that, okay? Of course, it should be a lot bigger than that, right? I guess, I don't know. So, on the ceiling of airplane, let's say we attach a string and a ball, right? So when the airplane accelerates, yeah, it will tilt backward. with an angle, assuming it's constant acceleration, constant force, okay? And it will stay there. Okay? Just like magnet pulling another magnet, this magnet is attached to a string, there's this magnet, right? Yeah, it will make certain angle and it will stop there. Okay? Or some positively charged ball with a string attached to the ceiling and you have negative charge capacitor right here, yeah, it will make an angle. It will tilt backward, right? At the angle theta, right? Yeah. But they're all analogous situation, okay? It's just force. So, and that kind of force is equivalent to wind force. That's why I was thinking about ether, okay? Yeah, I kind of re-encountered this concept of ether when I was reading this paper that kind of challenges Einstein's special relativity that I ran into, okay, about a week ago. I did mention that paper in our paper, okay, I did. But it was very very nicely written, okay. So yeah, we have some predecessors, okay. We're not the only challengers of Einsteinian special relativity theory. Yeah, some other people have done that before. Huh? When was this paper written? In my recollection, like 5 years ago. So it's fairly recent. Right? But before that gentleman, there was some other people too. Okay. Now, because if you are going to a battle, war, right? We don't want to go to a war alone. We need some allies. Okay, so it makes good sense. It helps to cite some reference. Okay, because they are more professional physicists than I am. I'm just amateur. Okay, and they are very serious about physics. Me, so and so. Okay, so anyways, so yeah, that paper written like 5 years ago that I mentioned in our paper. Okay, it does talk about ether. It's kind of archaic, kind of like outdated concept in physics, but I think it's very useful concept though. Okay, so for example, let's step back. Okay, our initial initial inertial symmetry theory. Yeah, I'm going that way, constant speed, but that's equivalent to the rest of the universe going backward when I'm standing still. Okay. Yeah. The extreme version of that is Earth spinning itself once a day. That's equivalent to the rest of the universe rotating around the planet Earth when the Earth is standing still. Okay, they're equivalent. Okay, yeah. Now, so me going that way is equivalent to the rest of the world going the other way. Okay, yeah, that's in inertial symmetry. Okay, when speed is constant. Now, when acceleration is constant, okay, me accelerating that way is equivalent to the rest of the world accelerating the other way. So, why do I feel like if I'm accelerating forward, why do I feel like I'm pulling back? It's because that's equivalent to the rest of the world going backward. So I feel this ether wind. It's a terminology in physics, ether wind. Let me look that up. Ether wind. Okay. Ether wind. Luminiferous ether. Yeah, Michelson-Morley experiment detecting the ether wind. Mhm. So that's a terminology that exists, but what we mean here by ether wind is not probably not the same as what our predecessor physicists used to mean. Okay, but that's fine. Okay, different definition, totally fine. So if I'm accelerating forward, and when the rest of the universe is standing still, that's equivalent to I'm standing still, but the rest of the universe is accelerating backward. That's the accelerative symmetry proposition or axiom. Okay? So when the rest of the world is moving back, accelerating backward, I feel this ether wind is blowing me backward. That's one way to think about it. How interesting, right? Yeah. Now, so Mr. Einstein thought that when the free falling object, let's say in space, there's no air, okay? Let's say on the the moon does not have any air, right? So a free falling object with some kind of acceleration, right? Would this object feel something? What does this object feel when it free falls? That's a very interesting question. Okay. Let's say on the surface of Earth, the Earth, okay, we have this weighing scale, right? So if I stand on top of the weighing scale, my weight, my mass would be something like, by now, I don't know, 160 pounds or 170 pounds, something like that. Okay. I don't know. It's been a while. Okay. So let's say it's 180 pounds, 170 pounds, whatever, right? But let's say bungee jump, okay, so that we don't die, even in the thought experiment, okay? Yeah, we got bungee jump, okay? And I scotch tape this weight scale on my feet, and I do the bungee jumping, not upside down, not headlong, but the right side up, okay? And I attach the my spring-based weighing scale on my feet, and I do the bungee jumping, okay? Then would that weighing scale read anything, or would it show zero? It will show zero. Why? Because that weighing scale is falling at the same time as I do in constant acceleration due to the gravitation. Okay? So yeah, Mr. Einstein's thought experiment on that regard was correct. Okay, so I will feel weightless when I'm free falling with bunch jump rope attached to me. Because even in our thought experiment, we don't want people to die. Okay, so we are pacifists, humanists. We value human lives, even in a fiction, even in thought experiment. Okay. Mm-hmm. But on the ground, when we put weighing scale, that weighing scale is not going anywhere. And if my body is on top of that weighing scale, my body weight, my body mass is attracting the planet Earth. So the weighing scale, the spring is being squeezed in between. So that's the measurement of a person's weight or mass. Technically, they are different, okay, in physics, but we're not gonna worry about technicality, okay? Technically, technically, weight is like Newton, like force. Okay, mass is just mass. Okay, so yeah, weight changes. If you are on the moon, you weigh less. If you are on Earth, you weigh more. If you are on the surface of the bigger planet, you will weigh a lot more. Okay, so that's the force concept. Weight, mass does not change. Whether you are on the surface of moon or Earth or Neptune, mass doesn't change. Okay, but weight does change. Okay, because weight is gravitational force. Okay, all right. We'll take 5 minutes break. Okay, and we continue to think about general relativity disproof. Okay, so but yeah, we'll just examine historical experiment and whatnot. Okay. Okay, so we are back, and this software is doing very well. That's good news. And so yeah, the troubleshooting worked. That's great. And now So when we feel the weight, okay, when we feel the gravitational force, I mean, as of speaking, I'm sitting down, right? So my keister, my butt, is feeling my upper torso's weight. Yeah, I feel it. I sense it biologically. Okay. Yeah, it's a skin, this neurons pressure sensor, right? Yeah, that sensation. Okay. But if I'm free falling with a bungee jump cord attached, and if I have something attached to my feet, like weight scale, whatever, okay? Yeah, I won't feel any pressure on the bottom of my feet, on my sole, because that object is also falling. The weighing scale is also falling as well. And the spring inside of the weighing scale is not going to feel my weight either. Why? Because we are falling at the same time. Okay, so uh, because beneath that spring of that weighing scale, there's nothing. It's just air, right? Yeah, resistance of air will ignore that. Okay, yeah. So that's why this spring in the weighing scale is not being squeezed in because there's nothing beneath it, under it, right? Okay, that makes sense. Mm-hmm. Very good. So let's step back a little further and talk about special relativity. Yeah, the simultaneity. Mr. Einstein again was partially right and partially wrong. Okay. Yeah, there is such a thing as simultaneity. Okay, simultaneity is not relative. Okay, so let's say two guys, A and B. Okay, they move, they synchronize their clock when they are together, and okay, and they move 100 meters the other direction with the same speed, and they stop at the 100 meter mark. Okay, and they flash the flashlight. Okay, and the third person, Charlie, is in the staying in the middle still. Okay, so in the beginning there's Adam, Brown, and Charlie. Okay, so Adam and Brown, they go away with constant speed. Okay, so their clock is still synchronized. Okay, because they're moving constant speed, even if there's such a thing as time dilation. Okay, now the flashlight. Okay, so Charlie, those two photons from Adam and Brown, it will hit Charlie photo sensor at the same time, okay, simultaneously. But let's say Daniel is between Charlie and Adam, okay, and then Adam and Brown, they shoot out the photon at the same time, but Adam's photon will hit Daniel's photoreceptor first, photosensors first, and then later on, Brown's photon will hit Daniel's photo sensor later. Okay, so in Daniel's mind, it was not simultaneous. Adam flashed, shoot out this photon first, and Bob Brown shoot out the photon later. Okay, because speed of light is limited; it's not infinite. Okay. Yeah, but there is such a thing as simultaneous, absolute simultaneity. Okay, so it's just that it's Daniel's misperception. Why? Because speed of light is not infinite. It's not instant, but it's limited, finite. Okay, so yeah, but there is such a thing as simultaneity, absolute. So Mr. Einstein got it like half right, half wrong. Okay, now what else? Yeah, back to general relativity. Okay. So if I'm accelerating forward when the rest of the world is standing still, is equivalent to I'm standing still and the rest of the universe is accelerating backward. So that's why I feel this ethereal wind. That's why I kind of push back like that, right? Yeah. Okay. Okay. That kind of makes sense. So it's equivalence between this ether wind force and accelerative this engine force. Okay, kinda. That's one way to look at it, at least. Yeah, we are exploring this symmetry, this equivalence concept uh, in acceleration world. Okay, constant acceleration setting. Okay, that's what we're doing. With Mr. Einstein, yeah, he asked the right question, but he didn't quite get it. All right, so he didn't quite get it right. So we are past this baton from Mr. Einstein, and we are continuing we're picking up where he left off. Okay, so that's what we're doing. Okay, yeah, unified field theory, kinda. Okay. Mm-hmm. We are trying to look for, we are looking for the equivalence between forces. All right, so okay. So I'm standing still. I mean, sitting still on planet Earth, right? So I feel the weight of my body on my feet or on my keister, okay? And this is equivalent to, let's say I'm just in the space, I guess, right? And maybe it doesn't have to be space, okay? Let's forget about gravitation first, okay? So if I'm sitting somewhere, okay, if the wind blows backward, then I will feel this pressure on my back against my chair, the vertical part of the chair. I don't even know how you call it in English. I don't even know how to call it in Korean. Okay, you have chair at this backrest, I guess, right? If wind blows backward toward me, then my back will press this chair. If I'm standing still and wind is blowing, there's some Jackie Chan movie about that. This hangar, this experimental place, laboratory to, yeah, these engineers, aerodynamic engineers, okay, aeronautics, right? In the hangar, right, when they experiment with airplanes, okay, design of airplanes. Yeah, some Jackie Chan movie have that. Okay, so yeah, if there's wind blowing, right, and I'm standing still against the wall, and the wind is blowing toward me, then my back of my body will feel the pressure against the wall, right? Because I'm being pushed by wind. Okay. Or let's say I wear a coat that is positively charged, and then there is this positively charged half of capacitor is in front of me, and behind the wall there is this negatively charged capacitor, right? And then my clothing, positive charged clothing, will pull me back, okay, against the wall. So my back will feel the pressure against the wall, right? Or it could be magnetic force, wind force, electric force, doesn't matter. Okay? So, this application of force that's pushing me back, right? Where I'm leaning against the wall, being pushed against the wall, right? By some, it could be gravitation. If the wall is the floor, yeah, I'm just lying down, okay? Yeah. Gravitational force is pulling me back, right? Because I have mass, right? Yeah. It's all equivalent, okay? Mm-hmm. Yeah. Yeah. So this ether wind analogy, it does explain. Okay, so if I'm accelerating forward, that's equivalent to the rest of the universe is accelerating backward, and I'm standing still. So I feel this ether wind. So that's why if I'm accelerating forward, my body is pulling backward because ether wind concept. Okay, so very interesting, right? I haven't thought about this before. Okay, so it's kind of first time, at least for me. Okay, so all right, we'll take 5 minutes break. Okay, all right. Yeah, we're making some good progress here. So okay. All right. Okay. Uh, so it's good that I didn't write today because I don't think I was ready. Yesterday I thought I was ready to write about this proof of general relativity, but thinking about it, I wasn't quite ready. But we are kind of getting ready. All right, so let me grab my whiskey, okay? Uh, uh, so, what is ether? Well, it's a I looked it up during my breaks. Okay, it's a hypothetical medium because what they say is in Newtonian physics, wave have to have a medium to propagate. So, but they know light propagate through vacuum. So they had to hypothesize this empty space vacuum is filled with hypothetical medium ether. Okay, so that's classical definition of ether. All right, not to be confused with the chemical in chemistry, ether. Okay, but it spells the same. Sometimes they put A in there in physics. Okay, but same thing. Okay, so what is ether? Let's think about it. Okay, when we are moving constant speed, in the air, we feel the wind blow. Like you're driving in constant speed on a highway and you open the window, then the wind blows. Why? Because the wind is air particles that is standing still. Relatively speaking, yeah, they are Brownian motion, of course, but mostly, let's say there's just standing still, okay, air. But you are walking or running with constant velocity. That's equivalent to you standing still, but the air is blowing toward your face with constant speed. That's the inertial symmetry, right? Yeah. So yeah, if you are standing still and there's no wind velocity, air is just clear and still, there's no storm, okay? It's a quiet day. Then you don't feel any wind because the air is standing still and you are standing still, okay? But let's say the storm comes in, okay? So there's a lot of, you are standing still but wind is blowing, so you feel the wind, okay? But that is equivalent to air is standing still, there's no wind, like zero wind velocity. Some nice sunny day in the afternoon, okay? But you are running, okay? So yeah, you hit all this air on your face. That's equivalent to you standing still and air blow. There's 10 meter per second wind velocity, okay? Or air standing still and you are running 10 meter per second. It's equivalent. You feel the wind, okay? On your face, right? Now, if you are in the vacuum out there in the space, if you are moving through constant velocity, you do not feel any ether wind at all. So that's the difference between wind force and ether force. Ether wind, you can only experience it when you are accelerating. Okay, so that's the difference between air and wind. I mean, air and ether. Good, we are making great progress. I don't know of any physicists who have given this kind of narrative. Maybe they have. I don't know of any. Okay? This discussion that we are having is very elementary, easy to understand. But I think it's brand new though. Okay? Yeah. Because elementary physics is all I know. Okay, so I don't know any more than that. Right? But so we are having this philosophical and also physical. We are doing philosophy and physics. Okay, very foundational, Abrahamic. Right? Yeah. We'll be the primogenitors of future generation, future physicists and philosophers. Okay, we are very being Abrahamic figure here. We are laying the foundation basically. Okay, getting back to the basics. Very good. Yeah. What else? How interesting, right? Ether, huh? Interesting concept. So ether is kind of like light. Light, it has no mass. It has no volume, right? Ether is like kind of same way, right? Ether exists in vacuum. Light does exist in vacuum too, between sun and the earth, between stars and the earth. Okay, yeah. And funny thing about light is this. In vacuum, okay, let's say there is star and there's the earth. Okay? And the light photon comes from the star and go through the vacuum and reach the earth, right? In the middle, let's say there's no molecule, air molecule whatsoever, it's just vacuum, okay? And if I am halfway in the middle between the star and the Earth, and I have this some panel blocking my side view, so I have this tunnel vision, and the photon is coming from the star and going to the Earth. I'm just in the middle with this tunnel vision. Do I get to see this photon? No. That's why photon is very interesting, right? When photon passes by in vacuum space, I don't get to see it. What do I see? Blank, darkness. I don't see photon passing by. Even when photon is a continuous this stream, like in highway traffic, from the star to the Earth, photon is constantly coming one direction from star to the Earth. Okay. So I'm having this tunnel vision with this wooden panel, right? But I don't get to see that traffic of photons. How interesting, right? Okay. So there's something in common between ether and photons. Okay. So I mean, originally ether was hypothetical medium for the photon electromagnetic wave, right? Yeah. I think it's still very relevant and interesting and useful concept, ether. Okay. So we are kind of resurrecting this concept of ether. Okay. Well, I kind of got this cue from this paper written 5 years ago. It's about challenging special relativity theory. Okay, written by a gentleman. I did look him up. Okay, so very serious physicist, professional physicist, unlike me. Okay, so very inspiring. Okay, so it does help read somebody else's paper. It does. It's very educational. Okay, but most of the stuff that we talk about here, we came independently. Okay. Yeah, it was. I just was taking cue because he was talking about ether, but not in this sense though. Okay. Yeah, he just mentioned ether, more traditional way. Okay, so I was like, oh, I remember ether, and the rest is history. Okay, we are doing our own things with ether. Okay, yeah. It's not from that paper. Okay, so yeah, I didn't peruse it. I didn't read it very carefully, like sentence by sentence. I just zipped it through. Very nice paper though. Okay, so because I don't have time to spend too much time with somebody else's paper. Okay, but yeah, there's some common denominator between our theory and his theory. Okay, so yeah, that was cool. Yeah, but he came up with he published like 5 years ago. Okay, but yeah, me and Einsteinian relativity theory, it goes way back. Okay, I've been thinking about this off and on as a back burner project. I have many back burner projects. Okay, so but all those back burner projects, yeah, I bring it here. Humanology. Okay, so it's just Einsteinian relativity is just one of them. Okay, yeah. Off and on, I think about the Einsteinian relativity for 2 decades. Okay. I think I got it right this time. Okay, disproving Einstein relativity. Okay. Well, we are not going to stop there though. We're gonna come up with alternative replacement substitute theory. All right. So yeah, we are past disproving special and general relativity theories because we already did so. Okay. Yeah, we are going beyond that point. Yeah. Good, good. It's just too bad I don't have any beer left. Hey. All right, let's stop and restart, okay? We'll take like 5 to 10 minutes break, okay? Thank you.